Good morning. Welcome to my videos on artificial intelligence methodologies and notions. In this first video, I will discuss the basic ideas of artificial intelligence. Let me introduce myself. My name is Sergio Focardi. I am professor at University of Genoa, Department of Engineering, DIME, where I teach risk management and financial engineering in the management engineering course. But my research activity is focused on causal artificial intelligence, creating and deploying causal models from data. Okay, so the first question, does intelligence need conscious thinking? Let's say that human reasoning is formed by streams of conscious thinking, conscious thoughts supported by unconscious cognitive activities that are responsible for discoveries and problem solving. Let's say when people hear or read sentences, they understand their meaning in some conscious way. When they try to solve problems, they direct their thoughts in various directions. If successful, a solution of the problem seems to emerge from unconscious processing of ideas. I mean, this is not a theory, it's the conscious experience of all of us. I mean, most people find it difficult to truly believe that the stream of conscious thoughts that form human thinking, human reasoning, can be simulated by purely mechanical processes. But this is what happened. First, the development of mathematical logic, and then the invention of computerized artificial intelligence have shown that some fraction of human thinking, but not all of it thus far, can be automated by machines that, by constructions, are purely mechanistic devices. For example, the surprising capabilities displayed by LLMs, large language models, lead many to believe that these machines reason like humans and are able to surpass them. And in this vein, many wonder if computers are going to develop thoughts and self-consciousness. So a little history on artificial intelligence will help. Let's say, to guide the discussion, I would like to summarize the conclusion of these three videos in a few words. So first, artificial intelligences are mechanical manipulators of symbols that do not explicitly depend neither on mental contents nor on meaning created by humans. Artificial AI does not mimic human conscious thinking. It's an engineering process that tries to mimic, but does not really mimic the process, mimics only the activity. The development of AI is due to four basic advances. First, the formalization of deductive processes, learning of functions and logical relationships from data, the ability to construct formal structures that represent the relationships between objects and concepts, i.e. the development of a formal semantics, and the ability to solve problems and create new formal concepts through a process of random generation of possible conceptual scenarios guided by heuristic and optimization. However, the creation of meaning through interaction with the real world is outside the possibilities of AI. The joint process of creation of theories and observation, which is typical of modern science, is currently beyond the possibilities of AI. So let's start with describing the automation of the processes. We are a long way for understanding conscious thinking. AI is the human engineering of processes that mimic some portions of human cognitive abilities. AI is not the representation of conscious thinking. We are a long way from understanding how human thinking works, creative thinking in particular, and we have no idea how to rationalize self-consciousness. We do not really understand the relationship between the brain as a physical object and the flow of conscious thoughts and experiences. I mean, as stated by Ernst Nagel, the philosopher Ernst Nagel, if we ever succeed, it will be necessary to make a huge conceptual leap compared to current science. Important to realize that we do not know what reality is. not only human thinking. Science studies only structure. Understanding thought implies understanding the reality of things. Huge conceptual leap. Let's now outline the main ideas that lead to the development of AI. The idea of automating reasoning has distant roots. The first step was to show that logical deduction is a formal game. The Catalan Ramon Llull, who lived between 1200 and 1300, conceived the idea that human knowledge could be organized as an encyclopedia of elementary concepts that can be combined through combinatorial mathematics. In the second half of the 17th century, the philosopher and mathematician Gottfried Leibniz formulated the hypothesis that human reasoning could be formalized and automated. Leibniz expressed what is, in his words, his dream, that in the future, if two philosophers were in disagreement, quoting Leibniz, it would be enough for them to take their pencils in their hands and say to each other, let's calculate. At the end of the 19th century, George Boole, Giuseppe Peano, and Gottlob Frege contributed to the axiomatization and formalization of logic and mathematics. However, it was the publication in 1910, 1912, and 1913 of the monumental three-volume work, Principia Mathematica, written by Alfred North Whitehead and Bertrand Russell, that really marked the birth of mathematical logic. Russell and Whitehead built a formal system in which logic and arithmetic could be formalized, and each theorem proved through mechanical manipulation of symbols. Now, logic in mathematics as mechanical manipulation of symbols. It's important to understand the scope of Russell's and Whitehead works. Principia Mathematica is a language in which arithmetics can be represented, and a series of mechanical manipulations on symbols that allow logical and mathematical theorems to be expressed and proven. Logical deduction does not presuppose conscious thinking, but it is expressed through sequences of purely mechanical symbol manipulations. Logic is a formal game of mechanical concatenation of logical and mathematical symbols. Russell also managed to overcome the antinomies of language, i.e. the contradictions intrinsic to language that have been discovered since antiquity. The formulation of mathematical logic is an achievement of enormous importance. In the years immediately following the publication of the Principia, it was thought that it would be possible to formulate logic and mathematics as complete axiomatic systems. But in 1931, Kurt Gödel showed that any formal system in which arithmetic can be formulated is essentially incomplete, in the sense that there are statements that are true but cannot be proved in the same axiomatic systems. Gödel's theorem is a result of enormous importance, because it specifies, in a sense, the limits of the process of automation. Gödel's theorem spurred many discussions. If there are more powerful axiomatic systems which are complete, and if we have to give up the possibility of mechanization of mathematics. In simple terms, giving up the possibility of mechanization of mathematics, logic and mathematics, implies that ultimately human mind is powerful than any mechanized system. There is no complete agreement on this question. There is a hierarchy of systems of different power, such as the Zermelo-Frank ZF axiomatic system, in which ordinary mathematics can be formulated. But demonstrating the completeness of these systems requires principles on which not all mathematicians agree. So, the invention of computers, and more generally of electronics, has changed the perspective of the automation of cognitive processes. Mathematical logic has been included in a broader philosophical technological process that has three objectives. One, to build synthetic processes for discovering deductions and solving problems. To get out of the purely formal syntactic sphere of symbolic logic and automate cognitive processes with real semantic content such as machine translation. To understand and possibly simulate human behavior, even in non-cognitive activities such as cycling and dancing with robots. In this video, we are not discussing robotics. Results have been impressive. The development of all intelligent technologies has never left the symbolic sphere. Even neural networks manipulate symbols. In addition to automatic inference, the fundamental mechanisms of AI are methods for the representation of knowledge and formal handling of meaning, learning, and synthesis of deductions in problem solving. Let's discuss. Knowledge and the handling of meaning. Knowledge bases are formal representation of knowledge, not representation of conscious meaning. They can be sets of formal sentences, graphs, networks of semantic connections, and more recently, neural networks. The knowledge of AI is completely abstract. Behind the AIs, there are ontologists, professionals who define and manage the structure and representation of the reality. The semantic of AI is formed by a set of assertions or logical relationships from which one can make deductions and obtain conclusions, but it does not convey any meaning in the human sense to the AI systems. The knowledge base can be expanded with learning process. Learning. For humans, learning is the process of acquiring new concepts, new facts, new rules, when we go to school, for example. For humans, learning can be conscious, for instance, when we learn new scientific topics, or unconscious, for instance, when we learn how to ride a bicycle. Machines learn patterns or functions from data and learn decision rules. There are two basic types of learning. Machine learning, supervised and unsupervised learning. In supervised learning, machines learn by examples. For instance, a neural network can learn a function from examples of the function. In unsupervised learning, machines discover structures hidden in data. For example, a linear discriminator learns how to divide a set of data in two groups with a plane. Synthesis, method of synthesis, i.e. the discovery of chains of logical deductions or the solution of problems, are based on the creation of several possible solutions from which the best one is chosen according to some criterion. So we reduce an infinite search space to a finite space that we can manage. Creating different scenarios and optimize for problem solving was the original idea of Allen Newell and Herbert Simon. The creation of possible scenarios is entrusted to the random generation of scenarios guided by heuristics. In other words, when a machine seems to discover a demonstration or solve a problem, it has actually randomly created many possible scenarios from which it has chosen the best one. For example, Cosa's genetic programming created new programs using genetic algorithms. LLMs are intrinsically random. Well, thank you for your attention. This was an initial presentation of the main ideas of artificial intelligence. Thank you for your attention, and I hope to see you in the next video.